In this video, we're going to find the small signal parameters of an amplifier called the common emitter with degeneration. Like the emitter follower, this is going to be a lot of ground that we cover, even though the slides will go quick. Also, like the emitter follower, you need to remember both the analysis and the results on these slides. So take it slow and work the math when you're asked. Fortunately, we'll see some of our small signal patterns in the common emitter with degeneration, which will hopefully lighten our mental load. The common emitter with degeneration is a common emitter with the bypass cap on the emitter node removed. So here we have RE to ground without the parallel cap. That means the emitter is no longer grounded. We'll find that the common emitters with degeneration have high Rin, fairly high Rout, and an AV that is the ratio of the collector resistor to the emitter resistor. That's exciting because it's easy to find resistors with precise relationships in their ratios, and also because our gain doesn't depend on GM. We expect that to dramatically enhance the linearity of the amplifier. However, RC over RE is often smaller than GM times RC, which is why RE is referred to as a degeneration resistor. The gain is degenerated relative to GM-RC because of RE. We're going to assume that RO is infinite throughout our analyses to simplify our math. Including RO doesn't change our results much, but it does make the math much harder. You'll get to examine the effect of RO on common emitters with degeneration in your homework. And that's going to be a slog, but being comfortable with wrestling with a tough small signal model is a skill I want you to practice, and that analysis will give you the opportunity. The first step in finding amplifier parameters is to draw a small signal model for the common emitter with degeneration. Pause the video and try drawing one now. This is my version. We set up our analysis to find Rin by remembering the test conditions for Rin. We set Rs to 0 so it doesn't add to the Rin that we calculate, and we set RL to an appropriate value so that any coupling from the output to our input of the amplifier gets captured by Rin. And I'm applying a test current source here to find the input resistance and encourage you to do the same. Given this setup, I'd like you to pause the video and try to find Rin. Feel free to use our small signal patterns if any are relevant. I've included my solution on the right. You'll recognize this math from two places, the emitter follower input and the RE boost small signal pattern. We find the emitter voltage by adding up the currents in the RPi branch and the GM branch and multiplying them by RE, and that's shown here because the current in the RPi branch is just given by IN. And then we note that the GM current is related to the IN current through the relationship that VBE is equal to IN RPi. Then we note that our input voltage is VE plus VBE, and substitute in our expressions for VE and VBE there, getting us the result that Rin is RPi plus beta plus 1 RE, which is about the same as beta RE. The one big difference here is that there's nothing in parallel with RE, which is not the same as our experience with the emitter follower. Now we're going to find the voltage gain of the emitter follower. We recall that we calculate voltage gain as the small signal Vout over the small signal Vin with zero source resistance and infinite load resistance. We set the resistances that way so that we're not measuring either the source or load divider by accident. I've set that up in the small signal model below. Note that the resistor from Vout to ground has gone back to RO parallel RE. Scratch that last sentence. Pause the video and try to find the gain of this amplifier. This is a somewhat new derivation, so I'm going to show it step by step. I started by finding that Vout is given by the GM generator current passing through RC. Vout is negative because the GM generator current runs up from ground to Vout through RC, so the positive side of RC is close to ground and the negative side is close to Vout. We note that the GM generator current is beta times I in, but we're stuck because we don't know I in. So we play the same trick that we played with the emitter follower, where we replace this detailed transistor representation with the generic amplifier model for just a second, because we're trying to find the current passing through this branch, which we could call IR pi in our transistor model, but is the same as I in our transistor model because of the way we're biased, where current can only flow into the base. That's convenient though, because it means that the current flowing in this resistor is the same as the current flowing in this resistor, which is therefore easy to represent as Vin over Rn. Substituting Rn into that expression gives us our gain, which is minus beta Rc over R pi plus beta plus 1 Re. And we can approximate that as minus Rc over Re. This super quick lab approximation is easy to remember, which I like. And it also doesn't depend on GM, which is really great because it eliminates our GM nonlinearity. That nonlinearity can sneak back into our full expression because R pi is equal to beta over GM. But as long as the beta plus 1 Re term is bigger than R pi, we'll have much improved linearity. So degeneration improved our linearity, which actually also comes from feedback for reasons we're not going to get into right now. Finally, we're going to find R out of the emitter follower. Our R out test conditions are an infinite load resistance, so that it doesn't steal any current from our output, and an RS that's normal for the amplifier. We're choosing to use a test voltage source for this analysis because it makes our life easier. Pause the video and try to find R out. Okay, R out is just RC. That's true because the GM generator is shut off when we ground V in through RS. There's a little bit of chicken-egg reasoning going on in my assertion that the GM generator is off. I'm saying that VBE is 0 because the GM generator is off, right? And there's no current flowing around on this side. But I'm also saying that there's no current flowing around on this side because VBE is 0. I confront that reasoning by asserting that if everything on the left side of this circuit is grounded, then there's no reason for nodes in the middle to not be ground. If you add RO to this problem, then VBE is no longer 0, and you have to do more analysis to find an expression for R out. However, that analysis is a classic example of where our small signal models pay off. I won't go over the solution to that in those videos, but encourage you to try finding R out with RO included, and small signal patterns in mind. So in summary, common emitters with degeneration are amplifiers with high Rin and a linear gain over large voltage swings. And we have derived the amplifier parameters for our common emitter with degeneration, which are given here. The input resistance is about beta Re, the output resistance is Rc, and the gain is about Rc over Re, with the exact expressions for Rin and AV shown here.